Good afternoon to everyone. Welcome to this section of the European Non-Associative Seminar, Non-Associative Algebra Seminar. And with a great pleasure, today I'm going to introduce the speaker of today, Ginevra Giordani from University of L'Aquila, that we will talk about central exponent in PI theory. Thank you very much, Ginevra.
Good afternoon, and thank you very much for your introduction. I'm going to share the screen so that you can see the slides. Just 1 second. Okay. You should see my slide, do you?
Yes.
Okay, just 1 second. I put it on full screen.
Yes.
Okay, we should be ready.
Yes, you can start whenever you want. Thank you very much.
Thank you all. So good afternoon again. Thank you again for inviting me and for your introduction. Yes, as Carla said, I am talking about the role of central exponent in PI theory, and I also will present some research advances in some specific context of PI algebras, and I will also spend some words about the non-associative cases. So let's just begin by a little motivation on why studying PI theory, where PI is polynomial identity, and then we will go on with the discussion about central exponent. So why do we study PI algebras? The motivation raises from both group and ring theory. There is a very important problem in group theory, that is Burnside problem, that you see stated here. That asks that if in a finitely generated group in which every element has finite order is necessarily finite, and then there is a translation for algebras and for division rings. So these problems are one of the main motivations. The others raise from ring theory. There is the Jacobson conjecture, that is about the Jacobson radical of a ring, and the Coet problem, that is about the relationship between one-sided nil ideal and two-sided nil ideals of an algebra. What do all these problems have in common? That they all have positive answers for PI algebras. So in the general situation is this one. For PI algebras, all of these problems have a positive answer. In the commutative case, they are completely solved, and of course, Coet problem is trivial because one-sided ideals are two-sided ideals in the commutative case, and the general non-commutative case is still unsolved, and where we have some answers, they are negative. So the long story short, PI algebras are in general non-commutative algebras, but they behave very well with respect to some problems and properties in algebra. We can say that in some sense, and we will see in which sense, they can be seen as a generalization of the commutative world, but we will arrive there. So now let's just explain what PI algebras are, and let's just see what is the central exponent, which is its role, and how does associativity plays with all of this. So let's just consider a base field, and we will consider it of characteristic 0, and I will explain you why in just a few slides. Everyone knows what an algebra is. It is just a vector space with an additional operation that makes it a ring. And of course, these three operations have some compatibility properties. The easiest example of an algebra is the algebra of matrices. And from now on, except otherwise stated, our algebras will be associative. And I will explain you why in some slides. So we will talk about associativity, but later. So for now, our algebras will be associative. So what are polynomial identities? Let's just consider a set of non-commuting, accountable set of non-commuting variables, and consider the three associative algebras of polynomials on that have variables in X and coefficients in our field F. We say that an algebra satisfies a polynomial identity if there is a polynomial in the free algebra such that it gives 0 for every evaluation in the algebra we are considering. And we will see some examples very soon. And of course, if an algebra satisfies at least one non-trivial polynomial identity, non-trivial means that the polynomial is not a zero polynomial, then we can see that the algebra is a polynomial identity algebra. Let's see some examples. As I promised you, commutative algebras are PI because the commutator can be written as x1, x2 minus x2, s1. So it is a non-zero polynomial that in a commutative algebra will always give 0 value for every evaluation because of, by definition of commutativity, of course. Another easy example are nilpotent algebras. So if an algebra is nilpotent with nilpotency index m, then we have that every product of m elements in that algebra will give 0 value. And so this is a polynomial identity, and so nilpotent algebras are PI-algebras. Another very, very important example are matrix algebras. It has been proved in 1950 by Amitzur and Levitsky that matrix algebras satisfy the so-called standard polynomial, that is this polynomial here. But we have to be careful because the algebra of matrices of order n satisfy the standard polynomial of indices 2n. So just this little consideration. And of course, we can see that our algebra M1 of F, that is simply F, satisfies standard 2, that is just a commutator. So it reduces to the case of the base field. So we want to study the identities satisfied by these algebras. We can denote the set of identities satisfied by an algebra as ID of A, and we see that it has a very strong algebraic structure because it not only it is an ideal of the algebra, and this is a very important thing, but it is also an invariant under all the endomorphisms of the free algebra, so it is a T ideal. And then it can happen that different algebras can satisfy the same identities. So we introduce the concept of variety, and the variety generated by an algebra is just the class of all algebras that satisfy the identity of the identities of generating algebras. So we want to study the ideals of algebra. Our goal is given an algebra to be able to tell which identities are satisfied by that algebra. But this is a very, very difficult problem, and it is completely solved only in very few and small cases, like 2 times 2 matrices. This case has a complete solution given by Drensky in 1981, and we have that the ideal of identities of 2 times 2 matrices is generated by these polynomials you see here, where this is standard 4, and it's the standard polynomial I introduced before. But as soon as we pass to 3 times 3 matrices, so not a huge algebra, we already don't know the solution. So the general case is completely unknown. Anyway, we have some results of about the ideals of identities of some algebras. Recall that we are in the associative case and with characteristic 0. So we have a very important result given by Kramer in 1987 that states that this ideal is finally generated, but if we consider a field of positive characteristic, this is not even true. And this is a work given This is a work by Bilov of 2010. So this is the reason why we are working in characteristic 0. Now, I just introduced multilinear polynomials, and in a few seconds I will explain you why. I think everyone here knows what a multilinear polynomial is. It is just a polynomial in which every variable appears exactly once in every monomial of this polynomial. An easy example is this polynomial, but also the standard polynomials are multilinear polynomials. And we can denote the space of multilinear polynomials with in n variables with P of n. But why I am talking about multilinear polynomials? Because there is a theorem, a very important result, that is called multilinearization theorem, that states that every polynomial identity is equivalent to a finite set of multilinear polynomial identities. So in order to study polynomial identities, it is enough to study multilinear polynomial identities. Why do we want to study multilinear polynomial identities? Because multilinear polynomials are easier to deal with. And so we can use this process to reduce our study to multilinear polynomial identities. As I said, this is still a very difficult problem in algebra, to say exactly which identities are satisfied by a given algebra. So we try to estimate them. We associate to an algebra a combinatoric object called the codimension sequence that is just it is a number, and it is the dimension over the base field of the space of multilinear polynomial modulo the identities, modulo multilinear identities. And easy examples are the commutative case. So even if an algebra is commutative, the only multilinear polynomial in n variables that is not an identity is this one. Why? Because if we switch the order of the variables, we have the same polynomial because the algebra is commutative. And it must be multilinear with n variables, so we only have this, we can only have this monomial. All the other ones are equivalent to that one, modulo identities. And another easy example is the nilpotent one, because as we have a nilpotency index m, then we have that every polynomial that has every multilinear polynomial in more than n variables gives 0, because every product of n variables gives 0 in a nilpotent algebra. And so we have that this number will always be 0 as soon as we reach the nilpotency index. Okay, so we want to use these codimension sequences to try to estimate the growth of multilinear polynomials that are not identities as the number of considered variables increase. So a priori, this number is factorial, because grows factorial in n, because if there are no identities, so if the algebra is not PI, we have the dimension of multilinear polynomial, of the space of multilinear polynomials, and this is n factorial. But as soon as we have at least one polynomial identity that is not trivial, of course, we have a very important result by Regev that states that this number is exponentially bounded. So as soon as we have one identity, this number grows much slower. And another very important result is given by Kramer and states that this growth cannot be intermediate between polynomial and exponential. So we can have polynomially bounded codimensions or exponentially, or we can have a codimension that grows exponentially. Now, a natural question is to ask if what happens when this n goes to infinity. So if this codimension sequence has a limit. This is a very famous problem called the Amitsur conjecture. It has been stated by Amitsur and proved by Giambruno and Zaicev, and the answer is positive. We have that the limit of the square root of the codimension sequence of an associative algebra of an associative PI algebra over a field with characteristic 0 exists and is a non-negative integer. This is a very strong result. Okay, but what happens if the algebra is non-associative? Now, up to now, I only spoke about associative algebras. So in general, there are counterexamples. So if the considered algebra is a Lie algebra, the exponent exists, but it's not said that it's an integer. It can be a half, for example. And the general case, in the general non-associative case, the existence of the exponent is not even guaranteed. There are counterexamples even about the existence. So for this reason, I have worked on associative algebras, even if there are some ideas also about non-associative algebras. But we will come back to this later on. Now let's get back to the associative world, and we introduce central polynomials because they are the main object of this talk. So what is a central polynomial? A central polynomial is just a polynomial that gives a value in the center, and we ask its constant term to be 0. And again, we can define the space of central polynomial that is a T-space. So it is a space that is invariant under the endomorphism of the pre-algebra. And we can define the central codimension in the same way as we did for the ordinary one, which is the relation between central polynomials and between this object and the codimension of identities. So first of all, we have to note that identities are central polynomials because identities will always give 0 for every evaluation by definition, but 0 is always in the center of an algebra. So identities are central polynomials, but it's not said that all central polynomials have to be identities. There exist also central polynomials that are not identities, and they are called proper central polynomials. And we have that these three codimension sequences are linked by this formula here. So why are central polynomials important? Because by studying them, we can recover information about the codimension sequence of the identities of a PI algebra. And we can study the relation between identities and central polynomials. We can also find out if in that algebra all identities, all central polynomials are identities or not. So we can recover a lot of information. This is why we want to do it. So I will present you my research advances in the case of superalgebras with superinvolutions, and I will explain you why. Why superalgebras, first of all? Superalgebras are a very important class in PI theory, thanks to this very important theorem of Kramer, because this theorem allows us to study the identities of a priori infinite dimensional algebra by reducing to study the identities of a finite dimensional superalgebra. And we can recover this information via the Grassmann superalgebra, or exterior superalgebra. It's called in both ways. This is the Grassmann envelope. This is G, the exterior algebra, or Grassmann algebra, as you prefer. And this is a finite dimensional superalgebra. So this is the reason why superalgebras are very studied, very important, and really studied in PI theory. So what is a superalgebra? It is just an associative algebra that can be split into two vector subspaces. It is just a Z2 graded algebra, and we have these relations between the subspaces. Of course, we can consider every algebra as a superalgebra with trivial grading. So the grading can be trivial, of course. Some easy examples. Let's consider the 2 times 2 algebra with matrices. We can give it the trivial grading, of course, and then the natural grading that consists on the diagonal to be the even part and the anti-diagonal to be the odd part. And we denote the the algebra of 2 times 2 matrices with this grading by M11 of F. And you will see why, because we can generalize it in this way. We can denote by MKH of F the superalgebra that has the diagonal blocks of order K and order H as the even part, and the anti-diagonal blocks are the odd part. So we can generalize this grading. So as I said, our goal is to study central codimension for superalgebras with superinvolution. Why? Because they are the graded generalization of algebras with involution. And this is really important for a lot of reasons. First of all, that algebras with involution are really important in mathematics in general, not only in algebra, but also in analysis, operator algebras, and dynamical systems. And by studying superalgebras with superinvolutions, we can recover information about the identities of algebras with involution. In which way? In the same way as we can do for the ordinary algebras and superalgebras. There is a theorem that is equivalent to this one, but with involution. So we can recover identities of an algebras with involution by studying a superalgebra with superinvolution. This is the reason. And lastly, superalgebras with superinvolution play also a very important role in the theory of Lie and Jordan algebras. So we have a lot of reasons to do it. What is a superinvolution? It is a linear map given on a superalgebra, such that on the even part, this is just an involution. And in the odd part, we have this -1. And this is the homogeneous degree of an element. So it is 0 if the element is in A0, and it is 1 if the element is in A1. Now, as the characteristic of our field is 0, we can split this algebra into 4 pieces, where A0 and A1 are already given by the grading, and every component is split into 2 parts, a positive part called symmetric part and a negative part that is called the skew symmetric part. The positive part is fixed by the superinvolution, and the negative part is composed by all the elements such that the involution gives their negative elements. So now, what do we want to do? We want to study, we want to define a PI theory for them. How do? We just want to consider the free algebra and the free associative algebra and give it the structure of superalgebra with superinvolution. How do? We split our set of variables into 2 sets, and we see that this algebra has a natural structure of superalgebra where this F0 is composed by all polynomials that have an even number of variables in Z, and this F1 is composed by all the polynomials that have an odd number of variables in Z. So the free algebra with superinvolution is generated by symmetric and skew symmetric elements of degree 0 and 1. So we have that a superidentity is the same concept as an ordinary identity, but when we evaluate it, we must respect the structure given by the map on the superalgebra. So the first variables are evaluated in A0 plus, the second set of variables are evaluated in A0 minus, the third one is in A0, A1 plus, and the last variables are evaluated in A1 minus. So they will always give 0, but the only admissible evaluations are the ones that respect this decomposition, where this decomposition, of course, is given by this one. Equivalently, we can define superidentities, the space of multilinear superpolynomials, and we can define the supercodimension sequence, and of course the concept of variety. There are the same concepts, but we are keeping track of the structure given to the algebra by the map, the superinvolution. So some easy examples. On matrix superalgebras, we can define two kinds of superinvolution. That is the supertranspose superinvolution, where this T is just the ordinary matrix transpose, and the orthosymplectic superinvolution. That is defined in this way, where Q is this matrix and this IL, it stands for the identity of order L. So, of course, note that 2L is not that the second index must be even, of course, because if not, we cannot define this Q. Then we can also define another kind of superinvolution that is called the exchange superinvolution. And to do it, we consider a superalgebra A, and we define its superopposite, that is just the same, it is an algebra that has the same graded vector space structure of A, but the product is given by this formula. And by doing this, we can define A plus A sub, that is a superalgebra called B, and we can define the exchange superinvolution of this over this B. So why I am introducing this? Because we will see that the simple superalgebras with superinvolution are made of this form. We will see it in just a few slides. So a very important result that will allow us to study central codimensions is the Weder-Bulmatsen decomposition theorem. That is an important result in algebra in general, and also in PI theory, and also in this context. So we have that an algebra, a finite dimensional superalgebra with superinvolution, can be split into a semi-simple algebra and its Jacob's radical. And this semi-simple algebra can be split into, can be decomposed into its simple algebras. And we have a complete characterization of these simple algebras that have the form I introduced. So the possible simple superalgebras with superinvolution in characteristic 0 are the first two are exactly the ones I introduced. So matrix algebras with these two kinds of superinvolutions. And the last two algebras, the last two possible kinds of algebras are have the form A plus A sub with exchange superinvolution, where in the first case, A is a matrix algebra, and in the last case, A is defined in this way. So two copies of n times n matrices, where this C squared gives. So, as I said, we want to study the central codimension sequences. Antonio Ioppolo in 2018 have proved the existence of the ordinary exponent for superalgebras with superinvolution. So this number, and this number is called the super exponent of a superalgebra with superinvolution, of course. And again, we can define central polynomials that are the same concept as before, but we have to evaluate these polynomials in the way I explained before. So we have to keep track of the decomposition that this map gives to the algebra. And again, we can define the codimension of codimension sequence of central polynomials. And we have that still holds this this formula, because we are these are the same concepts I introduced at the beginning, but we are just keeping track of this map. So what do we want to do? We want to study the central super exponent. So we want to ask ourselves if this limit exists. So, as I said before, the existence of the central exponent of a PI-algebra is an important problem, and it has been proved in other settings. For general associative algebras by Giambruno and Zaicev, For graded algebras by Daniela Lamattina, Fabrizio Martino, and Carla Rizzo. For algebras with involution by Fabrizio Martino and Carla Rizzo. And for superalgebras with graded involution by Rafael dos Santos, Antonio Augusto dos Santos, and Ana Cristina Vieira. We proved its existence and we studied its values for superalgebras with superinvolution. So our result is the following. I worked with Antonio Ioppolo, Antonio Augusto dos Santos, and Ana Cristina Vieira, and we proved that the central superexponent exists and is a non-negative integer. Then, if the superexponent of the algebra is equal to 3 or greater or equal than 5, then central superexponent and the superexponent coincide. In the other cases, it still exists and is a non-negative integer, but the central superexponent can have any value between 0 and the superexponent of the algebra. And why there is this distinction? Because of the Wedderbull-Maltsev theorem. What is? Okay, this one, because of this decomposition and because of the forms that these algebras have. So we have to study different cases, and we found out this result by dividing the proof into different cases that are completely explained in our paper. Moreover, we can do another remark that any superalgebra with superinvolution with the central superexponent that is strictly less than the ordinary superexponent can be decomposed into a direct sum of two algebras, where the first one is a commutative superalgebra with superinvolution, with the central exponent, with the superexponent equal to the superexponent of all the algebra. And the second one is, of course, generally non-commutative superalgebra with superinvolution with the superexponent that is strictly smaller than the exponent of the total sum. Now, I have worked with associative algebras. What happens if the algebras are non-associative? As I said, the existence of the PI exponent is not guaranteed. So we ask, does all this work make sense? Does this formula make sense? Because singularly, this object can still exist, because we can have identities in non-associative algebras. So we can define this in different ways, of course, but maybe we can do. There are some information about identities in some kinds of non-associative algebras. But of course, the existence of the PI exponent is not guaranteed. So what about the central exponent? The game is open. Now, here is the paper in which you find all the cases of our work, and I thank you for your attention.
Thank you very much, Ginevra. Nice, really nice and interesting talk. So, there are any questions for our speaker, or comments, or curiosities?
May I ask a question?
Sure, of course.
In the associative case, is there any connection with Gelfand-Kirchhoff dimension? I mean,
is there?
Is there any connection with Gelfand-Kirchhoff dimension? I mean, does it play any role? There is a dimension, it's called Gelfand-Kirchhoff dimension. I am wondering if is there any
I honestly don't know, sincerely. Okay, I understood, but I honestly don't know.
Thank you.
You're welcome. I'm sorry.
Any other question or comments? I have, yes, a remark. But in a non-associative case, actually, the answer is given for Lie algebras, finite dimensional Lie algebras. The answer is For that special case, we have an
Yeah,
answer.
but the general case is still open.
Of course.
Okay.
But that
Yes,
one is
no,
really
sorry.
big one.
I meant the general case. Yeah, for the algebras, we have way more theory than the general non-associative. Okay.
Yeah, so for
I didn't specify, sorry, but yeah, you are right.
so for non-associative case in the meaning non-associative algebra, not associative. So in general, the answer is open. But for some classes like Lie algebra, finite
We have way
dimensional
more
Lie
theory,
algebra,
yeah.
For finite dimensional Lie algebra, we have some information, especially the exponent, the central exponent is not. Okay. Any other comments, remarks? Okay, if there are none, thank you again, Ginevra. It was really nice talk, really interesting. Thank you very much. Thank you to everybody.